along with the same material, is used to then introduce the sample into a gas chromatograph. So the advantages of this over many other tests is that it is, has a high sensitivity for volatiles and semivolatiles. There is minimal to no sample preparation necessary. Essentially, all you have to do is get a sample of the appropriate size to use for your sample vials. There's minimal or no alteration to a standard gas chromatograph setup, and by standard I mean what's typically used in a conservation science laboratory for analyzing materials taken from works of art. So basically meaning anyone who has access to a GCMS could use this technique to analyze exhibition storage materials. Very rapid analysis time, and you have the possibility, which I'll talk about later, of quantitative analysis. So here's a schematic of a manual holder for these fibers. This is essentially analogous to a syringe, and it's used just like a syringe. This hollow metal tip contains a fiber, which is a fused silica core, so very similar to the glass that's used for the columns inside a GC. And it's similar, it's the inverse of a GC column. So all of the business part of a GC column is now on the outside, and these layers, these can be different materials, have different affinities for different types of volatiles and semi-volatiles. So you select an appropriate coating for your fiber to use for your sampling. And then you essentially can take this and use the iron tip or the stainless steel tip to plunge through your septum and then expose the fiber to the materials that are being off-gassed from your sample. This is just showing it in the being inserted into a GC, so kind of sort of the scale of it. There are obvious drawbacks. You first of all need a GC, so it's much more expensive than the Oddy test. And making further analogies to an Oddy test, you cannot analyze all samples simultaneously, as in the Oddy test, where you can have multiple vials or multiple chambers set up for your samples. You have to analyze these things sequentially. And the other issue is that certain small volatile species of interest, and I'm speaking mostly of formaldehyde and acetaldehyde, are very difficult or impossible to analyze directly on typical GC columns for conservation. And so one needs to make modifications to the just a straight SPME analysis technique. So for small volatiles, formic and acetic acids, those you can analyze using a standard straight SPME fiber, but because these acids are kind of too polar for these columns, you don't get good resolution, and so quantitation is more or less impossible, but at least you can see them. However, formaldehyde and acetaldehyde, even though they might be in your sample, just using a straight SPME fiber for sampling, these things are too volatile to stick to the fiber, and you can't then get them onto the GC. So derivatization in both cases, changing these species, these molecules, to something else that is less volatile and or less polar will help in the analysis. So the technique that I use in the lab is this on-fiber derivatization. So there's no additional sample prep required. All you do is expose the fiber beforehand into a vial containing this derivatizing reagent in a vapor form. So you load up your fiber with this material, and then you sample your material of interest. And so what it means is that some of these really high volatile materials that you're interested in, formaldehyde, acetaldehyde, can then be transported from your fiber across the room or from a different part of the gallery, museum, to your GC. And if you are careful, you can load up multiple derivatizing reagents on the same fiber to analyze for different species at a time. I'll just say right now, I've not done that. I've not found that to be necessary at this point. So the one that I use, another acronym, this is probably the longest acronym you've seen so far in the conference, PFBHA, allows for detection of formaldehyde and acetaldehyde. And it's very, very stable, and so it's made up by mixing it with a little solution of water, and the vial is very, very stable, and I've used one. I keep checking it off and on, and it's given me the same exact profile for years now, so it's very, very stable. And this is what the chemical is. I won't go through and say it all, but it's essentially a benzene ring, and the reaction, this is the reaction end of it, and this reacts with aldehydes and ketones. to form what are known as oximes. So I'll be referring to these PFBHA, formaldehydes, and acetaldehydes throughout the rest of the talk. So sample prep. Again, it's very, very minimal. Here is a board of materials that I was recently given by our design and installation department for materials that are being considered for exhibition cases. And the requirement is they need to be small enough so they'll fit in my sample vials. So it's basically a 3/8 inch square by about 3/4 inch long things. I can also have sheets, usually 2.5 inches on a side, that can be wadded up and put inside the sample vial. This is also a very useful tool for sample prep. It's actually, I had been looking for these very, very expensive maceration things and whatnot, and came across this $40 KitchenAid thing, and it's stainless steel, and it cleans out really easily, and it's really powerful, and this was a really, really hard piece of ebony, and it took care of it in about 30 seconds, so it's excellent. It also works on all kinds of other materials too, so foams of various kinds, you can get those up. And here are basically some of the sample vials with sample bits in them, so you get an idea of the size of that. The other form that you would want to perhaps consider is that many of your materials in an exhibition case, for instance, you're only having one side of that material being exposed to your sample, to your work of art. And so I've set up a situation where I've chopped off one of these sample vials. I've got a hole cutter from Home Depot that I cut my material of interest with silicone grease. I vacuum silicone grease, which itself does not off-gas, so that I'm sure that all I'm getting in my analysis are things from the sample. So the current GCMS setup that I've used for several years now alternates between these two different auto-samplers. One is more or less a very simple one, which I'll show a picture of, and one is a very, very fancy one that does all kinds of movements and things. Sample holders are heated to 60 degrees Celsius, which is just coincidental that it matches up with the Oddy test temperature, and that's only because that's as hot as I could get. The original sample holder that I was using was up to 60 degrees. And I do that only to encourage things to off-gas at a higher rate so that I get higher concentrations of fiber. And the best fiber thickness that I've found that's the most versatile is this 100 micron thick polydimethylsiloxane. There are a variety of films out there on these SPME fibers, and this is the one that gives the best sort of general response to most of the materials for conservation issues. And then we have an old Saturn GCMS, and for those of you who do GCMS, these are very, very standard conditions that we use for our instrument. So I mentioned the auto-sampler. Is remotely related to quantitation, even semi-quantitative measurements. You really need to have an auto-sampler, and you kind of see why, because you've got one of these holders, you've got to figure out how to hold your sample vial, you have to put your fiber in at an exact rate, exact amount of time, have an exact amount of time to get back to your instrument to insert it. Otherwise, your quantitation can be off. So I have relied on an auto-sampler ever since. This is our simplest auto-sampler with just 5 slots for vials. This bath that I use, circulating water bath that I use to keep that at 60 degrees. And this is our, showing some sample vials. And this is our fancier unit. Has multiple spaces. This robotic arm will then load up the fiber first, or actually what it will do is pick up your sample first, put it into this chamber for heating, and while it's heating, it will load up the fiber with the reagent, the PFBHA, go back in, sample what's inside the oven, and then it will inject it into the top of the GC. So it all gets done remotely. And so that brings up quantitation. You can get really, really excellent, very reproducible, very linear results with this technique. And I'm just showing, this is simply the reagent that's used, the PFBHA, showing the amount of time that I've exposed the fiber to it. So from about 2 seconds up to about 70 seconds. And the amounts that comes off is quite linear. And you can see that there actually are error bars. I've done it multiple times, and it's quite reproducible. Very, very good. And so what that translates to in reality is I selected a 12-second loading time, and in this case, I then have sampled my material for 60 seconds. And you see then when I do the analysis, I have a peak that corresponds to the unreacted reagent, a peak that corresponds to the reacted and created PFBHA formaldehyde, and then I've done it at 5 minutes and also at 10 minutes. And so the conditions that I've selected for this now are a 12-second loading time and a 5-minute sampling time. You see that I basically am not getting rid of any more PFBHA unreacted off the fiber. So I'm trying to minimize the amount of unreacted material on my fiber and maximize my amount of sampled material. So all that about quantitation. There are obstacles and actually disadvantages, I think, to quantitation. The problem is if you're trying to make correlations with what you actually have in your exhibition case, for instance, it's very dependent on the proximity of your object to that material that you're testing, because in a closed environment you don't necessarily have good mixing, and so it's mostly by diffusion. So if you've got your object separated from the material that you're testing by even a few inches, it's going to be very different than if it's sitting within an inch or actually in contact. So it's the way you interpret your results for quantitation depend very, very much on how all of this is occurring. It also depends on how you prepare your sample. If your sample is only a surface sample that is in the case, or if you need to have something that's fully inside the case, you need to figure out exactly whether it makes sense to do this complete tearing up of your sample so that you have good surface to volume ratio of exposure. And then again, this is completely helped by having an autosampler, but this can be an issue, and it's actually quite critical to have an autosampler to do this properly. So that being said, I generally have found that quantitation is not necessary for the most part for these kinds of tests, because we're more interested in whether it's a good material or a bad material. And if it's a bad material, we don't want to argue with it and decide, okay, it's okay as long as it is 6 inches away and not 2 inches away. So we don't want to get into that. So if it's good or bad is sufficient. So the test procedure that I use, samples are weighed, placed in a 10 ml vial that you saw, 12-second exposure to the PFBHA. It gets exposed to the headspace in the vial for 5 minutes, and then it's injected, and that then from the time of injection to the end is about 22 minutes, and I leave the fiber in the GC for a minute to make sure that everything is desorbed from the fiber, so it's a clean fiber for the next analysis. So the total sample total analysis time is 27 minutes. So much faster than the 28 days of the Oddy test. So I'll give some examples briefly here of coatings, adhesives, rubber gasketing, textiles. I'll skip wood, and then polyethylene and PVC storage materials, and then a couple of interesting miscellaneous items. And so I'm going to show you a lot of GC traces here. No mass spectra, which is good, but just a few spectra. So coatings and adhesives. This is showing, and all these are pretty much the same. I'm showing 5 minutes into the run and up to 15 minutes after the run is started. So I'm not showing the complete run here because the first part is kind of boring and the last part is definitely boring. But this is to show this, I didn't label this, but this is the unreacted PFBHA material, and then this is it reacted with formaldehyde. So this acrylic masonry filled, even though it's acrylic, it has an appreciable amount of formaldehyde present in it, and it has a series of things that are being off-gassed, which are cyclohexane, so saturated C6 rings with straight chain hydrocarbons attached to them that are acidic. So they're acidic, but they have otherwise few sites of attack or oxidation, meaning that it's not good that they're being off-gassed, but it's not as bad as some other things that could be off-gassed from these materials. But this obviously is a bad thing to be off-gassed. Here's a comparison of two different hot melt glues. Hot melt glues range all over the map in terms of the components that are in them. This is one that passed the Oddy test, consistently passed the Oddy test, and this is one that did not pass the Oddy test. And for this one, you can see it's because of the huge amount of BHT, butylated hydroxytoluene, that was present in this. But this one that did pass the Oddy test, there are quite a number of things that are being off-gassed, but with this GCMS technique, you know then what these materials are, and these are all straight-chain hydrocarbons, so effectively non-reactive materials. So if you're okay with very, very tiny amounts of effectively wax floating around in your chamber and perhaps depositing, perhaps not depositing on your object, then this would be a fine material to use. And in many cases, because it's a hot melt glue, it's a very thin bead, it's a very small amount, it's a very small amount that would be exposed in an exhibition case. There are times in which this would be fine to use, I think, even though it is off-gassing materials. Rubber gasketing. Again, two different examples. We have one here, an EPDM rubber, which is off-gassing a huge amount of formaldehyde. And then another one, the neoprene rubber, which contains chlorides, but it's also off-gassing a bit of the straight-chain hydrocarbons. So this is one of those neoprene rubber seals that we allow for things that are not that sensitive, for instance, stone materials if they're in a case, or for other materials that are not art-containing that require rubber gasketing throughout the gallery. And again, I should point out that a lot of these things I'm showing, and we'll talk about it again at the end of the day in our next talk, about how I'm testing a lot of materials that would not normally be tested by a conservation lab, but again, we're trying to get a handle on everything we have in our museum and try to eliminate things that could just as well not be in our museum, if we can find substitutes that work as well. Some textiles here, 3 different classifications that I tend to come up with when I do textiles. I think these are all runs of 6. So there were 6 or so that had this exact same profile, 6 or more that with this one, and 6 or more with this. And the differences is in between these two is the amount I'm assuming of washing. There are all kinds of things that go into textile manufacturers. And so some of these prepared textiles I'm assuming have been washed in a certain way to reduce the amount of BHT, but they still have BHT. And then there are other materials, other textiles that we use or have used or have sampled that basically have nothing that's being off-gassed from them. Plastic sheeting and films. Here's a bad sticky PVC sleeve, and we get some straight chain hydrocarbon, and because it's sticky and coming into contact with things, even though this itself is not reactive, obviously you don't want to use this for anything that you want to preserve. And then we have some comparisons with archival PE sleeves and coroplast. So again, it's just polyethylene, no sites on the chain where you can have any kind of oxidation occurring, so these have been known to be quite stable, and indeed the SPME test shows that to be the case. There also shows that there are no plasticizers in these as well, because this would also show up plasticizers too. So a couple of miscellaneous items. I've talked about these 2 things for years now, and they're both samples from, well, one is actually from NMNH, another acronym, National Museum of Natural History, and the other one is from NMAH, National Museum of American History at the Smithsonian. This was from a diorama at NMNH that was on display for probably 20 years before they took it down, and it was shoved in the back of their lab. So I got a slice of the styrofoam from that and looked at that. So this is, at the time I did the test, it was at least 20 years old, probably older styrofoam. And SPME test shows huge amounts of styrene still being off-gassed from that, and also a measurable amount of BHT coming from that. And then here's a sample of asphalt. I don't actually have a photograph of it, but this was something that NMAH called me in desperation because they had done multiple Oddy tests on this material and it had not failed, and they really thought that it should fail. because how can you have asphalt in a, anyway, it just didn't seem right. And so they gave me a sample of it, and I did the test, and indeed, there is some formaldehyde that's being given off, but there's also a huge number of additional acetaldehydes and ketones and probably acetone-type materials all being given off at the same time from this. That's what all of these peaks are. So there's a huge amount of material that's being off-gassed, and there are all kinds of reasons why the Oddy test would have failed in this instance. But this was enough proof for them so that they could go and say, no, we can't have this in our display case. So I'll just show you this slide. This is, I don't like this slide, but it at least gives you some points of comparison to something that is familiar, the Oddy test, and showing that SPME in almost all cases is in agreement. So when the Oddy test, when a good, reliable Oddy test that has materials that you know should fail does fail, SPME shows yes, it will fail. In places where Oddy tests can find no problems with the material, in most cases the SPME will also find no problems, or it will find additional things that are in there. And in those cases I've called it inconclusive, meaning that it's actually giving you a lot more information than the Oddy test could ever give about the identity of those materials that are coming off of the object. And so just in conclusion, SPME with on-fiber derivatization is useful in determining the suitability of exhibition and storage materials. It's rapid, reproducible, and you get identification of all of your volatiles that are coming off. There's still the issue of not being able to identify easily and well and reproducibly things that don't derivatize on the conditions that I use, such as formic and acetic acids. I can see them when they come off, but it would be nice to have something that would give me nice sharp peaks that I could then think about quantifying. And chlorine, I can't really test for chlorine, but we also, which I didn't mention, have our mount makers do a copper wire flame test for chloride-containing materials. We usually get that information from SDSs, but there's also a way of figuring out whether you do have chloride in things, and you get a nice green flame when the copper is burning. And then the issues with quantitation need to be addressed, although I think at this point, for our purposes, it's become a routine test in our lab. We don't really need quantitation, but it might be nice at some point to have a point of comparison where we're having input from our design and installation department about a material that they'd really, really like to use, and we have used a material in the past for some other purpose, and it showed some off-gassing, but not much. And so if we could relate the two materials together for quantitation and come up with a way of either proving to them that it really won't work or saying, okay, fine, in this case, it actually might. So I think quantitation requires a lot more work and a lot more discussion to actually employ it successfully in these situations. And then finally, just acknowledgements. Everyone in Scientific Research Department and National Gallery, and then Beth Ann and Merv and Julia for providing samples that I used in the talk, and also Beth Richwine at NMAH for the asphalt samples. So thank you.
Just a reminder that we'll do questions during the panel session at the end of the morning. So do write those questions down. We'll get to them right before lunch. Our next speaker is Eric Breitung. He is a, whoops. What did I do? No, you're fine, I got it. I guess I'll keep going. Eric Breitung is a research scientist in the Metropolitan Museum of Art's Department of Scientific Research. He received a PhD in chemistry from the University of Wisconsin-Madison in 1999. Go Badgers. In his current position, Eric investigates techniques for evaluating preservation and construction materials for the movement, display, and storage of art. He is also developing novel anti-tarnish coatings and is interested in degradation mechanisms of polymeric materials. Welcome.
Hi, yeah, so I'm going to talk about something that's very synergistic with what Chris just discussed, which is looking at how do we assess materials that we're using with, I call it paper-based, but really all the organic materials that are in the museums. Right now we're using an Oddy test which uses metals, and it's pretty ideal for assessing whether you would put something in with a coin or a bronze sculpture. And so I'm trying to find a simpler test that we can use that might say, well, what if you look at something we're going to put in with a book or maybe a piece of bone or some other organic material. I did all this work while I was at the Library of Congress. I just moved to the Met 6 or 7 months ago. So if you're looking for me, that's where to find me, but this sort of all gets credited to the library. I wanted to show you our version or the library's version of the Oddy test, since you've seen others, just to see the variety and why people seem to get different results, because everyone does it a little bit differently. You can see there's some odd stuff here. I put glass beads around this beaker to keep it from moving around in the oven. If the coupons hit the glass walls, then they tend to corrode preferentially there where water meets and condenses. And we use this soda lime glass jar. Most other people have converted to Pyrex, et cetera. And then do the same amount of time and temperature, and then look at the metal coupons to assess whether they're really corroded or not. Obviously this one is very corroded. And here's sort of examples. The other thing I want to mention is the library uses metals that are at least 99% pure, but probably more pure. The Oddy test, as it was changed or recommended in 2000 or so by David Thickett, was at least 99.9%, but changing the purity of those metals can also affect how sensitive the test is. And something that was mentioned, I think in the first talk, was that the Met had looked at soda lime glass and how it becomes acidic, or basic, I'm sorry, during this test. It was actually done by Greg Smith in Indianapolis. But I redid this because I hadn't heard of that. He gave that as a talk in 2008. And so I wanted to just prove it to myself. And so I took one of these hazy jars. This one has been used, turned alkaline. It sort of has glass disease in it. And I washed it with soap and water, and then used one that had been used that didn't turn alkaline, so maybe that didn't have as corrosive of a material in it or whatever causes these to turn hazy. And then I looked at new jars straight out of the box, just washed with soap and water, as well as tried silanizing the surface, which we use in analytical chemistry to keep things from absorbing onto the glass walls, to see if that could have any effect. And then looked at this Pyrex jar, which is something I'm considering using for future Oddy tests, if I could ever find a piece of glassware that I could use as a beaker inside that fits through that opening, which I'll probably just make on my own, I guess. But anyway, the bigger point is that these top four all become alkaline, as Greg found with the ones he tested, and the one in Pyrex doesn't. And so that's why everyone's converted to these Pyrex jars. And again, highlighting the point that is the sensitivity of the test changing because we're using these different types of jars, or is it not sensitive enough to matter? And these kinds of questions people have been asking for 15 years, I think, and everybody getting slightly different results because of it. So the METS test is very similar, primarily because Joe Bamberger is still there. He was been there volunteering as an ex-scientist, or a retired scientist, I should say, for 15 or 20 years, and has published work to make sort of this 3-in-1 test. They use silicone grease all over the place on this lid to keep it from evaporating the water. The library doesn't do that, but the library ends up throwing away a lot more tests because they dry out. So if a test weighed the same as it did when you first put it in the oven, then we said it didn't leak, but we threw a lot more away. Whereas this, the grease tends to work. We use a little less pure metals than the library, and they were only running single runs. Now we're moving to some minor changes using duplicates, which I highly recommend. A new jar for every run, so at least if we are creating in an alkaline environment, it's the same amount each time. And we store all the metals in intercept bags, or at the library I would put them in a vacuum oven, so that we weren't corroding the metals over months before we use them in the test. And in the future, I basically plan to mess with the museum's test a little bit to try and improve it and increase the repeatability. And to Chris's point, we are also moving towards SPME and doing exactly what he's doing, and feel like we need to continue doing the Oddy test because it's so ubiquitous in the field. That said, I'm hoping to one day transition away from it as well, just because it's not as reliable. But for organic materials right now, I'm interested in finding out what materials that we're recommending with the Oddy test do to organic materials. Are we producing degradation of organic materials that we're unaware of? And so the question is, what is the Oddy test actually telling us? How do we know that? Well, I started out by looking at what are the corrosion products, and from those corrosion products, can we tell what's causing those corrosion products, or what mechanistically should cause those corrosion products? So to do that, we looked at a series of materials, which I don't need to go through. This was for a particular project at the library. And then we did X-ray diffraction of the corrosion products that were on each of these coupons. So we did all of them, the silver, lead, and the copper. I'm presenting one slide on the lead, but note that we were able to do this with all of them, and sort of look at the literature to find mechanisms for what would cause these chemicals to form. So here's your example. We had carbonates, oxides, and carboxylates in these lead coupons. And all of the mechanisms that we found pointed to either there being some oxidant, often it was oxygen, but an oxidant, and or an acid present to make any one of these materials. You'll find in modern materials, though, there's a lot of other stuff in there. And this is what Chris is pointing to with his SPME test. And so the real question is are these things affecting organic materials the same way they do these metals? If we can look at a metal coupon and it's corroded, we can also say, well, it's corroded, so therefore certainly the paper would be corroded or degraded. Then maybe the Oddy test is fine if we could get it to be repeatable. Or can we look and find oxidants and acids with this SPME test and basically say the same thing? So the test that we chose to use was sort of an adaptation of something that Shahani had developed in 2001 at the library, and that was to take Wattman filter paper, and this is a Pyrex tube. It has that same silicone O-ring and inert cap that I showed in the first slide of jars. And we put in a gram of just Wattman paper. Wattman paper is 100% cellulose, so there's no other fillers, there's no lignin, no other additives. So we're really just looking at cellulose degradation. And then our preservation material, in this case, it looks like it's a glue that we peeled off of, we formed into a film and peeled off and stuck in this jar. We pre-equilibrate at 50% relative humidity, so there's not an addition of water, but there is moisture present. And then we heat it very quickly, 100 degrees Celsius at 6 days, which the paper conservators I presented this to have said, whoa, that's hot. Is that really realistic? And we've done tests at 90 degrees, where now it takes 14 days to run the test instead of 6, and got the same results. And then we went down to 60, and it would take, it was something like 13 or 15 months projected out to get to the point where we got the same amount of degradation. So just to give you a perspective. But that said, we were getting the same degradation products regardless of the temperature that we were using, which really meant that we were off-gassing the same amount. We were just really accelerating that process. What were those products? Cellulose, fortunately, is a fairly simple molecule, fairly stable, and can break here to make monosaccharides through hydrolysis. And you can take a lot of these oxygens and oxidize them, break the chain open through various mechanisms and make aldehydes, ketones, and acids. You can really do a lot worse, which we will hopefully never get to that regime where we're basically burning the compound. But the problem with this test, unlike the Oddy test, is we can't visibly often observe those degradation changes unless the paper starts to yellow. We do see some of that, but if we relied on yellowing, even if we use scientific instruments to view it, we'd be missing a whole boatload of information. And so, much like Shahani's test, we're able to take the paper and extract it into water. So we take our test sample after we age it, put it into water, extract whatever is in there that's water soluble into the water, and all these sugars should be water soluble. as we know from drinking a lot of soda and coffee. And then I've chosen ion chromatography to analyze this because I know that I can see sugars with ion chromatography fairly easily without a lot of sample preparation. Those who have different equipment, like a GPC or even a GCMS like Chris's, there are ways to get the same information out. So you don't have to buy a bunch of different instruments, but it would require just a little bit different sample prep to get the same kind of information. And if I had an LCMS, I probably would have used that, but I didn't have one. The cost difference is also quite different. The IC is more like $50,000 to $75,000 to buy, and a good LCMS, they're going anywhere from between $150,000 to $600,000, depending on what you want to see. So anyway, here's the data, the type of data we were seeing, and this is just to test, under those aging conditions, what am I doing to paper just with air in the vial? So it's aged Wattman with air and unaged Wattman. And you can see that the pink is the unaged Wattman, has fewer peaks and smaller peaks. And so I am doing some damage to the paper. So I'm in a regime where I am damaging the paper in some way. And I'll show you sort of what I think some of these peaks are in the next slide. And then if I see these peaks get larger, then I can say that it's attributed, when I put a preservation material in the jar, then I can attribute that degradation relative to the control, which is always aged Wattman, and make a judgment on whether it's damaging, the preservation material is damaging the paper. And so we ran a bunch of standards, which I won't go through, but the major concept here is these are all simple sugars. And these come out of the column first. They're smallest. They have the fewest number of hydroxy groups. As they get bigger and get more hydroxy groups on them, it takes longer to come out of the ion chromatograph. And so this is a 2-ring version of cellobiose. Here's a 3-ish ring version of mallotriose, and so on. It would just keep going out to the right if we had longer oligomers. And so at least I know what I'm looking at using those standards. They come out at very particular retention times. And so this is arabinose, and this is glucose. Glucose being really the primary degradation product of cellulose when it's in hydrolysis at the end of the chains. And then this is, I think it's galactose that we use as an internal standard. So that peak should stay very similar in size for all of the runs, unless we somehow are making galactose out of cellulose. But in this case, you can see we're not. And we can also look at these as sort of examples of the kind of chromatograms we get, this being the control. And here's one that looks identical to the control that would have been something that passes our test. And here's something where these peaks got larger than the control, and that we would say would not pass our test. Much like the Oddy test, the degrees of separation between permanent, temporary, and unsuitable are arbitrary. We had to make arbitrary levels as well that we based on a lot of the experiments that we did, and it seems to be working. But we have not done physical testing of the paper to correlate these arbitrary tests to some physical damage in the paper. The best I'm probably going to be able to do is GPC, which is another way to look at paper degradation that's well established, that looks at how at breaking those chains in the middle of the cellulose, and that correlates to physical embrittlement and so on of paper. And that's sort of underway. So I won't go into this, but we have an arbitrary scaling, and we look at basically ratios of the control to the peak areas of the peaks at A, B, and C, retention times. So now I'm going to show you a couple of examples of what we found. We looked at those 22 or 28 materials, did an Oddy test and an IC test for both, and found a range of results, which I'll show. So here's the Oddy test for this material. It was a binder board, and it basically had an identical IC spectrum between the control and the sample itself. So we would call it permanent. We can go okay to use this with organic materials, and in fact with non-organic materials. It seemed to pass both tests well. Here's an example. I probably wouldn't be standing here if all of them looked like that last slide. Here's an example where we didn't see that, right? So here's an Oddy test that showed, no corrosion really on the, or a little bit it looks like, right here in the middle on the lead. So maybe that was a temporary, some people would say, well, that was hanging over the edge of the beaker, so we shouldn't count that corrosion. Again, arbitrary assessment of the coupons. So permanent or temporary, and then here we have those larger peaks at A and B. C is not much difference, but the numbers, once you calculate it, you can see would be unsuitable. There's a lot more peak area there on this book class IC test, so we wouldn't use this in with our collections, even though the Oddy test said, yeah, go ahead and use it. So to answer that question, do preservation materials have the same effect on paper versus or organic materials as metals? The answer is probably not. And out of that set of materials that I looked at, 20% of them turned out to give a different result. So the ones in red here are a couple of examples of things that gave different results with the Oddy test and the IC test. I hope to expand this list and repeat all of these and so on to really verify how significant of an effect this is. But even with one, it's enough to say, well, maybe we should be looking at this issue. And then on top of that, we got some very odd chromatograms that gave us very large peaks. There are two here, there's one here, it's very large relative to our A, B, and C. And here there's a bunch of stuff. Maybe this is a larger peak, this one definitely is. And this is plastizote, I think a foam people kind of stopped using. And you can see here the IC test said, yeah, sure, it's fine. If you look at A, B, and C, and the Oddy test said, yeah, there's no corrosion on these metals. But the question is, much like Chris is asking, what's this other stuff, and does that affect the object, even in a way that might not have to do with degradation or corrosion? And then the same here, this might be the material that's causing all this corrosion that we can see, or this degradation of the paper. But we don't know until we figure out what that is, right? And so what else can we learn from the IC test is, well, maybe we can learn which materials we should do more testing on to see that there's significant other off-gassing materials there. And I would argue that based on the way that I'm sampling or extracting, the IC test would never be the perfect indicator for that, but it does tell you when there's something significant going into that water that we're extracting. So this is identical to what Chris was talking about. It's the SPME fibers. Here I'm doing something slightly different where I'm taking the fiber and dipping it directly into a liquid. So that's the water extract that I filtered off all the paper fibers. So it's whatever dissolved into the water, and I can sample that way. It's a really versatile and great technique. And this is closer to the way that Chris was using it, though I'm not doing any pre-functionalization. I do use several different types of fibers that have different absorbers on them. To see if I can catch everything. And then I won't talk about this technique. This one allowed me, number 2, allowed me to look for the sugars that are very hard to get through a GC without functionalizing. So I functionalized those to make them more volatile, but not really necessary. It was more to prove to myself that I was seeing that those were actually sugars. And so I think this is the same material that I showed a few slides ago, where it was both the IC test and the Oddy test gave the same result, but if not, it's giving a very similar chromatogram. But here's an example. I wanted to do a case study, and I chose this last night based on the Museum of Fine Arts Boston's case example, where they were looking at a silicone foam as well as they had an adhesive, but a foam that was off-gassing something of concern. So this would have passed both my IC test and the Oddy test, but something is absorbing into that paper, and it's acting more or less like a sponge. And so that would be, as Chris said, sort of floating around your case, and it might not cause degradation of your clay pot, but maybe it will form these beautiful crystals as it combines with something else. We don't know until we know what that is. And so I went ahead and did those tests very similar to Chris with SPME or SPME. And of the water extract, remember this is only the stuff that's in the paper and is soluble in water. So it had to act like a sponge, go into the paper, and then come out into the water, and found more or less that these are relatively inert compounds and that there was no paper degradation. That said, this can, over time, potentially turn into an acid if you have the right conditions. Acetone is not a great thing to have around, but it's not going to cause necessarily corrosion or paper degradation. And then phenol also can change its form and do things, but it's more or less an alcohol and will, in all these cases, be volatile. So if you're sweeping air through your case, you can remove these things. The headspace SPME, or SPME, gave us more information, and one of the compounds that was mentioned yesterday was benzaldehyde, and so I did see that with this silicone foam. But even more interestingly is that we found long chain and lots of long chain siloxane. So Chris's the adhesive showed long chains. Hydrocarbons, this is kind of the same thing, except there are silicon-oxygen chains instead of carbon chains. This is the kind of stuff that they used in potato chips to fry them a long time ago, and the food just went right through us. I don't remember that. So pretty inert stuff, but it can grab onto some of our vitamins and things. It still can migrate and affect the physical properties of whatever it's touching. And so in our case, this is where looking case by case kind of matters. We were interested in storing for very long term. We had just bought 5,000 special cases for storing wax cylinders, so these things that hold recorded sound. And they wanted a piece of foam that those could lay on to keep them from hitting the very hard material that they had chosen for this container. And so this foam was going to be in direct contact with the wax cylinder. And in that case, here we have a lot of stuff that's going to migrate into the wax cylinder and maybe onto the wax cylinder. And because it's not reactive, you won't see a change in maybe the hydrocarbon lengths of the wax or things like that. But you might change the glass transition temperature or the softness of that surface. And here you have an object where you need to rub a big metal ball through a groove on that surface to play it and get the information back on it, out of it, otherwise it's fairly useless. And so, knowing that this is here and figuring out, should we try and remove that before we put the foam into the 5,000 containers? Use a vacuum oven or maybe heat this foam samples up and blow air across it. We could get rid of probably a lot of this material while also getting rid of some of these things that we definitely know we don't want in there, like benzaldehyde. This linear siloxane is probably not a degradation product of a silicone. In the kinds of conditions that we store these wax cylinders or silicones in, they're not breaking down a lot into oligomers. And they're fairly stable molecules. As we know, they're hard to get rid of, they're hard to react with things. But again, they can make things softer. And so I'm sort of promoting this, as well as the GCMS, SPME techniques, as a way to thoughtfully consider what materials we're using and how to use those, because we probably can't get manufacturers to make the perfect material for us. I had tested 2 other polyethylene foams along with this as possibilities, and they either failed the IC test or had things like free radical generators in them from their polymerization process. And so this silicone actually turned out to be the best of the 3. And then finally, I don't know how much time I have left, but finally, I thought, well, IC and GCMS are very expensive techniques relatively. Is there a way to look at these paper samples from the IC test, kind of like the Oddy test, where anyone, even at a very small, maybe even private conservation lab, could evaluate these things and say something about whether they're useful materials or not? And so I know that UV Vis is relatively inexpensive. It's still kind of expensive at $5,000 or $10,000, but people are coming up with cheaper and cheaper ways to do this. And there has been literature out where they've done paper analysis on old paper, looking at relative to new, and then doing accelerated aging tests and seeing that the UV absorptions increase as we age papers. And so, and then some of these will tail into the yellow region, and that's why we sort of get this yellowing of paper. But we should be able to detect these UV absorptions earlier than when we see yellow. And so I did this with reflective fiber optic UV spectroscopy, and that's what's going on here. It's this little box. It's maybe, I don't know, this big, and it puts out light and then detects it, and we can reflect that light off of the paper and assess its UV absorption. And so I did that with a bunch of materials, all these materials, in fact, that we studied. And then I categorized them on one chart where I said I took the Oddy test in this case, categorizations of permanent, temporary, and unsuitable, and overlaid them with color coding. So red is unsuitable, green is permanent. And you would look at this and say, well, there's really no correlation. We can't use UV vis. And I agree, there's no correlation. You don't see all the green clumping together or all the red clumping together. But when I did this with the IC test and used those same curves and categorized or made these same color referencing on the chart, you can see that there's a much better correlation where the green ones are down near this black curve. The black curve is just our control. And so and then the yellow curves are slightly above that. Could I actually differentiate the temporary from permanent in this case? No. But can I differentiate a lot of these unsuitable ones? Probably, yes. And so this is a 1-minute test. It costs maybe an eighth of what an IC test costs. And if you don't, especially if you don't count my time, it's an eighth. And then that's just for the equipment, I guess. And so we could have said right off the bat, we don't need to run the IC test on this and probably don't need to run GCMS on it. Both sort of expensive techniques that require a lot of equipment and time. And so this could be, and I think it's here, a nice screening method. Do I need to do more of these? Yes, I'd like to get hundreds of materials onto this chart so that we can really say whether we've got a good correlation or not, or how consistent this type of degradation is. And that is something I'm setting up at the Met along with a system that's very similar to Chris's and the IC test. So in summary, I have sort of 3 main points. That I actually think the Oddy test is reasonable. It's been working for the most part. We don't have a lot at the same amount of degradation of materials that we see in cases as we used to. We've gotten much better at this. We use the Oddy test to get that information, and it's working pretty well, especially for metal materials. But for paper-based materials, we don't really know. You can't see the degradation if it's happening. And I know the library's mission was to preserve things 400 years past the end of the Republic or something like that. So, you know, we have these lofty goals of preserving things for a very long time. And with paper, you can't see the crystals forming on the surface like you can on a bronze sculpture or a coin. And so this might allow us to figure out beforehand what might cause that kind of degradation. And I am a full believer that combining the paper test with a SPME or SPME test will allow us to make much more thoughtful decisions about where and how to use materials. Are there pretreatments we can use? Can we get rid of some of these things that are just byproducts of producing them before we use them and and basically end up with an inert material doing that extra little step? Because it was said, I think yesterday, quoting I don't remember who, that it's much more efficient to put in the right material and that's neutral than to deal with it after you've sort of ruined an object and have to conserve that object. The cost difference is significant and worth taking the extra step first in the first place. And then possibly the UV spectroscopy might be a good pre-screening method along with this IC test. So you could, if you didn't have any money and just wanted to buy some Pyrex tubes and put in your Wattman paper and a UV system, this may be a way to just do some pre-screening. And at some point, I would guess it's going to take another year and a half, should be able to publish something on that, whether it's working or not, on hundreds of materials. I'd like to thank, I didn't do all this work, it was mostly interns and fellows. Marcia Wiggins, she's now at Delaware getting a PhD with a focus on preservation science. Aaron Ullman's, he did a lot of XRD in 3 or 4 months, ran through all those samples. It was a lot of good work. Linshi Wen was a high school student at the time, and she did all the mass spec work. Super impressive. And she's now getting a PhD in New Jersey. I'm trying to remember the name. At Princeton, yeah, sorry. Yeah, if there was another school, maybe it could have been Rutgers, I guess, I don't know. So Carlos is working with me now. He's just gotten his BS in chemistry and is looking for some experience in any field, and I've got him sort of just learning techniques. So he did all the pH work. And then Joe Bamberger, who helped develop that 3-in-1 test, is still, poking at me to not change it, and he says it's fine. So, which in many senses he's right, that the little changes I'm making don't change the sensitivity that much, and it's a decent predictive test. So I appreciate his input on this. And the conservators and scientists at the Library of Congress were very helpful and just in consulting. Lynn helped me a lot with the XRD technique, which hopefully we'll publish at some point as well. It was just a kind of a great way to get the corrosion products off of these coupons. Anyway, thank you for your time.
Our next speaker is Greg Smith, the Otto N. Frenzel III Senior Conservation Scientist at the Indianapolis Museum of Art. Dr. Smith earned his doctorate in physical analytical chemistry at Duke University in 2000 and completed postdoctoral work at University College London, the National Synchrotron Light Source, and the National Gallery of Art here in Washington, D.C. His current research includes studying pollutants in the museum environment, the analysis of modern colorants and plastics, understanding pigment degradation processes, and improving pedagogy at the art-science interface. Please welcome Dr. Smith.
Thank you. Let me begin by saying how pleased I am to be here to tell you a little bit about the successes, but also the challenges that we've experienced in our materials testing program at the Indianapolis Museum of Art. So the IMA is one of the 10 largest and 10 oldest encyclopedic collections of art in the United States. It has about 56,000 works of art on a 154-acre campus, and that campus comprises both the Fine Arts Museum that you see here, as well as 2 historic house museums and a 100-acre art and nature park. So I came to the museum in 2010 to set up the first scientific analysis facility, which we opened in the spring of the following year. And almost immediately we were called upon to help vet materials for 2 large projects that were happening at the institution: the relocation of our African collection, as well as the creation of a whole new suite of galleries focused on contemporary design. So these were large-scale projects that involved people from across the institution, and it really gave us an opportunity to hone our skills in materials testing. So materials testing has always been a part of conservation at the IMA, but when you throw in an analytical research facility, suddenly you can start doing a lot more varied tests, as well as being a lot more rigorous in your scientific analysis. So the laboratory is set up to do most of the major forms of chemical analysis with microscopy and chromatography, spectroscopy, thermal analysis, and accelerated aging. So my background in materials testing began about a decade ago when I was hired to be conservation science professor at the graduate training program at Buffalo State College. And in order to better prepare our students for this opening field of preventative conservation, I instituted a new course called The Science of Preventative Conservation, which really focused on those chemical aspects of the interaction of artist materials with pollution and light, relative humidity, and temperature. And so this was a very hands-on practical course. The students were doing a lot of realistic laboratory exercises, doing Oddy testing, doing light fastness testing, environmental monitoring, and such. So one of the first things that I was asked to do when I got to the IMA was to review their materials testing protocols. And I got a sense from the conservators that there was a lot of dissatisfaction with that process, as well as a lack of confidence in the results that were being generated. So, and I apologize, one of my transparent TIFF files did not show up on the computer here, but at the time they were running a variant of the Oddy test. So this was being conducted in a 1-liter beaker. There were large slabs of commercial stock metal being used as the coupons. These were suspended by paper clips over top of a beaker of water. And then the material under test was tied directly to those coupons using either twill tape or thin sheets of Tyvek. So there was a lot of room for improvement in this protocol. So at Buffalo, we had adopted the British Museum's 3-in-1 Oddy test because this is a published test. It's been thoroughly studied, and every attempt has been made to standardize it in order to improve its accuracy and its precision. So the test is run in one of these large Pyrex boiling tubes, and an airtight seal is made with the silicone stopper. You put 3 slits in the bottom of it, and you can wedge your high-purity metal coupons in there. suspending them over top of the material that you're testing, and then another small Pyrex test tube is going to hold the water that provides the relative humidity. And so then this would be put in the oven for the 4 weeks at 60 degrees. So once we instituted this at the IMA, I could see the confidence building in the testing protocol, and our results do actually begin to become more consistent. One of the other benefits of this approach is its compactness. So at this point, we can now run dozens of these tests simultaneously in our oven, which allows us to do replicates of both the controls as well as the materials under test. And of course, that also will build confidence in the results you're generating. Well, I don't think I have to say much about this. A lot of people have mentioned this. These are actually the jars that got us on to that idea that the glass was being attacked during the Oddy test, and it shows you the alkaline environment that's being generated, but a number of people have already mentioned that. Now, one of the arguments that's often leveled against the testing in the conservation department is that it doesn't fit the time scale for design and fabrication of these large projects. And so it's not unusual that we get someone coming into the lab with a bit of material that's going to be used a day or two later, and they want you to run a fast Oddy test. And so technically there is no fast Oddy test, but using some microchemical tests, we've been able to do a preliminary analysis in relatively short order. So you've already heard about the Beilstein and the sodium azide test. We also run 2 color change reactions, very quick 1-hour tests. So chromatropic acid will turn this deep purple color in the presence of any material that generates formaldehyde like Delrin. The iodide iodate test turns this caramel color in the presence of organic acids like you get from hardwood species. So we keep those reagents prepared in the lab at all times, and we're able, from the time we get the sample, about an hour, hour and a half later, we can generate at least a preliminary result. So adding to that arsenal of tools that we can use to assess materials and then increasing the rigor of our Oddy testing, I consider that to be one of the early successes of the marriage of the science lab and the conservation department. But I also want to talk about some of the challenges that we faced. And so almost immediately after opening the laboratory, we were called on to begin vetting materials as part of this large relocation of our African collection. This collection had been displayed since 1989 in a sort of geographical layout in these galleries that had the ochre-colored walls, either hanging on the wall or displayed on these thin platforms that kind of snaked their way through the gallery. And so because of the natural palette of many of these African objects, they just kind of dissolved into that environment. And then also having them out here in the open, either on the walls or the platform, exposed them to an awful lot of museum dust and the interaction of our visitors. And combined with those very fragile surfaces, this was a real conservation nightmare. So in the rethinking of the gallery space, there was a decision to present these less anthropologically and treat them more like fine art. So we were going to emphasize their forms over their functions. And as a result, the designers went with the sort of interiors that are more typical of our contemporary art galleries, but this really allowed those objects to pop and to be emphasized. And we were also able to encase more of the objects in wall cases and vitrines to better protect them. Well, the organization of the galleries changed as well. So instead of sticking to a geographic presentation of the objects, we went instead with these themes, these universal themes that transcend the sort of arbitrary boundaries that were imposed on Africa by the European settlers. So things like power and ancestors and the royal arts. And as a subtle visual cue to signal the transition from one of those thematic spaces to the next thematic space, the designers chose these amazingly beautiful exotic African hardwoods to inlay all the platforms and the cases and the vitrines. And so this gives you an idea of those wood species. They're all very beautiful. There are 6 species of wood and 7 different veneers being used. And so all of the objects having to do with power were displayed alongside these mahogany veneers, and then everything having to do with the royal arts were displayed on top of these ebony veneers. And so naturally this raised the eyebrow of the conservators because it tends to violate one of our principal tenets of preventative conservation, is that we don't willingly put hardwoods into enclosed spaces with artworks. But we were asked to Oddy test these materials. So we began by Oddy testing the veneers, and they all failed spectacularly, the way you might imagine. So the lead coupons crumbled and turned white and dusty, the copper discolored. And so then we were asked to retest them, but to do it in the way that they would be used in the gallery. So they're mounted to this Med-X, and then they're coated with 2 coats of our standard acrylic urethane sealant, which is Fura 260. So we Oddy tested those, and they all failed again. So then we were asked to test it for a 3rd time, but to double up our protective layers and put 4 coats of the acrylic urethane sealant on the hardwoods. And this time, 4 of them failed, but 2 of them got temporary ratings. So that's better, but these were permanent installations, and so it would probably be several years before they would be refreshed, and so technically we shouldn't be putting temporary things in there. But at this point, we were already almost 4 months into the design phase. There really wasn't a plan B, and there was already a significant investment in these veneers, so there had to be some sort of compromise. And the decision was made to allow the veneers, but we were going to monitor these cases very closely. So polished lead dosimeters were included, and if they began to show any corrosion, then we would have to think about actively filtering these cases or perhaps going in and removing those veneers and then replacing them with something far more benign. Well, it's been 3 years since we opened these spaces, so it's fair to ask, how are we doing? This is an example of one of those lead dosimeters. It doesn't photograph very well, but a little bit of the polish is being lost along the borders, but we're certainly not seeing the sort of powdery white corrosion that is evidenced in the Oddy test. And when you open up these vitrines, you also don't get that sort of stringent vinegary smell that you might expect of an enclosed hardwood. Instead, the smell is really that of earth and smoky campfires. And so it's obvious that it's these objects that are really dominating the environment of those cases. And in general, when you look in the cases, it's a lot of African hardwood sculpture, African masks made of wood, African shields made of wood. And so the veneers themselves are probably contributing a relatively small relative amount of surface area of exposed wood. So is this an ideal installation? And the answer is probably not. It's a compromise, but I think that is pretty typical of how a lot of this happens in museums around the world. Well, we've talked a lot so far about studying materials in order to protect our collection, but what about studying materials to assess their durability? And this certainly became evident in our American Paintings Gallery, where a few years after the installation, we loaned an artwork and saw that the wall paint had faded considerably. So that now loaning a picture meant that we not only had to find a replacement that fit thematically in the gallery, but it also had to be the same size, or else now you're going to see this faded area out here. Well, Benjamin Moore stood behind their product. They refunded the price of all the paints, but for anybody who does this, you know that the cost is not in the materials, the cost is in the labor. And something like this, with a couple hours of experimentation in the laboratory, we could have predicted this and avoided it. So going forward, all of the coatings that we're using in our permanent installations will be tested not only with the Oddy test, but also tested for light fastness. So I can jump back to those veneers because the same principles are in effect, and this was recognized by the conservators and the fabricators at the time, that any wood that is exposed to light is going to darken, and anything that's covered by a riser or by an artwork is going to be protected. But the thought at the time amongst the designers was that these are going to be objects that are rapidly changing, so there won't be the opportunity to build up those starkly contrasting lines. But these photos are actually taken just a year or about 8 months, I think, at the first rotation. And so it's pretty severe and pretty rapid that this develops. And again, these are the sorts of things that now we're prepared to pick out and to identify using techniques in the laboratory. So one of those would be the microphadometer, which was originally produced to make analyses of light fastness of artworks, but the same principles are at play with the construction materials, so we can use it there as well. You've got this intense xenon light source that's delivering light to a pinpoint on the surface of your object or your material. Another fiber optic is picking up the scattered light that your eye senses as color, and we're measuring that color to generate charts like this, where we can track the color change as a function of exposure to the light source. And these are relatively short 10-minute experiments. Now we run a series of fast-fading standards that are the yardstick by which we can compare to the artwork or to the material under test. Blue wool 1, 2, and 3 fade at known rates. And so blue wool 1, for instance, will be noticeably discolored after a little less than a year at 5-foot candles. Blue wool 2, slightly slower. Blue wool 3, slower still. And so here are the measurements of those hardwood species. The onigre and the babinga fade between blue wool 2 and 3. And in fact, almost all of the wood species, I'm saying fade, they actually darken. So it's just measuring a color change. They darken in this area. The only exception is the ebony, which is a little more stable and darkens far more slowly. And so our galleries are lit between 5 and 15-foot candles. So it's no surprise that these things would noticeably darken within, say, 6 to 9 months. Well, on the heels of our African installation, we also created a new set of spaces in 2013 dedicated to contemporary design. So this is 11,000 square feet of gallery space, over 400 objects being exhibited there. So this makes it some of the largest galleries of this type in the country. At the time, the designers and fabricators were looking for a material to replace the wood products that we had been using previously for gallery furniture and casework. And so conservation was brought in immediately to begin vetting materials that could possibly be used. And we looked at a lot of polymeric materials, but we had also been hearing a lot about this Sintra expanded PVC board that other museums were using in their casework. So we acquired some of this for testing. In fact, what we got was Celtec. And we Oddy tested that and used our microchemical testing, and it passed all of those. It met the requirements of the designers and the fabricators, so we began using this to create these cases for the design galleries. Now, we were pretty surprised 3 months after the opening to notice that some of our highly polished silver objects were beginning to develop this warm tone and eventually to tarnish. And this was despite all the safeguards that we had put in place. So we had been looking carefully at the case materials, everything going into the case. These were not hermetically sealed, but they were tight-fitting cases, and they also had adsorbents in them to try and mop up some of the pollutants. So it really left us scratching our heads as to what was going on here. Well, having access to a full scientific laboratory, we could pull some of those objects and just confirm the nature of the tarnish. Here you can see an example on these Michael Graves salad servers. Using Raman spectroscopy, we simply bounce the laser off the surface of the tarnish. We get its scattering spectrum that you see here at the top. It matches very nicely with silver sulfide. So it confirms what we had always thought, that this must be some sort of sulfur-based pollution. So at this point, we were wondering, is it inside the case or could it be from outside of the case? And that led to a study of the entire museum environment trying to figure out the sources of pollution. And so we're using these relatively inexpensive corrosion classification coupons. So for 15 bucks, you get a copper and a silver dosimeter, and along with that, you get the analysis after a 30-day deployment that is chemically specific and identifies the nature of the tarnish that develops. So we deployed these across the museum, and I'm just showing you a map of our third floor that contains the design galleries and just the data from the silver corrosion. So the size of the circle tells you the thickness of the corrosion layer, and then that places it in a classification for the environment. And by looking at a large area, we were hoping that there would be trends which would point you towards a particular source of pollution. And so there are definitely some hot spots here. These could perhaps be explained by the fact that they're close to exits to the museum, so you're getting a lot more of outside air. This one in particular is right over top of a Japanese rock garden, and so there's probably a lot of opportunities for pollutants to have been introduced through that. In general, though, the pollution levels were quite manageable for most of the museum, so these African and fashion galleries would be rated clean or pure. But on average, in the design galleries, the values were higher. And in instances where tarnished objects inside cases were tested, and then right outside the case we also tested, the pollution levels were always higher inside the case. So we're still analyzing this data. We're about to do a second round of testing as the museum enters its winter humidification cycle. But we're already chasing down some of the possible leads here. So for instance, there's a chance that it could be coming, the pollution could be coming from the casework itself. So these PVC expanded boards have to have a heat stabilizer in them, and one of the favorites is this mercapto tin compound, which we know exists in the Celtex. When you take this pure chemical at a relatively low concentration and put it into an Oddy test vessel, you certainly get tarnish appearing on both the copper and the silver. It could also be the objects that are in those cases. These are relatively sparsely populated cases. They tend to have inorganic materials in them, glass and ceramic. But we started to look at residual polishing compounds as maybe being a source of pollution. Now, we don't use Tarnex in the conservation laboratories, but these objects were donated to the museum and they might well have been previously polished. Well, the acidified thiourea in Tarnex, if you Oddy test that, you definitely get corrosion on both your copper and your silver coupon. Finally, thinking about the museum environment, we introduced some boiler water to humidify the air, and in looking at the treatment of those boilers, there is a small amount of sodium bisulfite that is added to those boiler systems as an anti-corrosion agent. Now, this is not a volatile chemical itself, but if you get the bottle of the batch chemical and smell it, there is a bit of an odor, and so there's got to be some unreported volatiles present in that chemical. Now, this is a greatly exaggerated test, but if you dump a bunch of that chemical into an Oddy chamber, you can definitely get corrosion of all three of the metal coupons. So this is a top priority for us to figure out, and we're chasing down all of these leads. So we're doing a lot more studies of Centra, and for the time being, we're not constructing any of our casework out of it. We're actually moved to painted plexiglass for most of our casework now. But we're holding off on using this until we get a little further into our research. We're also looking closely at the objects that are coming out of these cases, and anything that goes back in is going to have to be lacquered for additional protection and more sorbents added. And then finally, we're looking at replacements for the sodium bisulfite. There is an erythroborate chemical that is a relative of like vitamin C as an antioxidant, and so we'll explore some of that and talk with some of our colleagues about other options. Well, the tarnish was one of those challenges, but I want to end with a positive note, some of the other successes that we've had in our materials testing program. So there's been a lot of discussion of what's good and what's bad about the Oddy test. And like others, we have been looking into ways to supplement or augment our Oddy test. And like Chris spoke about this morning, we're using GC mass spectroscopy as a way to analyze the volatiles directly. We're just doing it in a slightly different way. So instead of using the SPME needles that you introduce into the headspace over and collect and absorb and concentrate the pollutants, we're actually using the pyrolysis furnace that is available at many of the conservation labs around the world to do a technique called evolved gas analysis. So we put just a couple milligrams of material into this little crucible. We then sink that down into a heated furnace at 115 degrees. We wait 30 seconds for the furnace to fill with volatiles, and then we pump them onto the cooled tip of a GC column so that they all condense there. We then begin the chromatographic run, which begins to separate out those compounds. We spray it into a mass spectrometer. You get the characteristic fragmentation that allows you to identify each of the pollutants. So the advantage for us for this technique is that it's about 30 minutes between the time that we get the sample and the time that we have our report. Also, we're avoiding that intermediate step where you have to collect on the SPME fiber or derivatize. Instead, we're generating the volatiles and immediately dumping them onto the GC for analysis. So one of the first things we looked at was polyester polyurethane packing foams. A number of people have mentioned these. They were studied at the Met previously because they found objects that had been stored for a period of time in these foams had little white crystallites on them. So they did an Oddy test of the foam and then used SPME needles to analyze the headspace inside of those jars. And they identified these alkyl morpholines that are catalysts used in the manufacture of the foams as being the source of the white crystallites. Well, here is data that we generated in one of our EGA runs. A 15-minute run on a bit of this foam identifies the same set of homologs of alkyl morpholines that were identified at the Metropolitan. And then we wanted to do something a little bit different in line with what Chris was talking about. Can we quantify these? Well, you can buy 4-ethylmorpholine, and we use that as a surrogate. So we determined a response factor for our instrument and then applied that response factor to these and quantified them as 4-ethylmorpholine equivalents. And so here are our values for the quantitation. Now, if you look at our percent errors, they're kind of high, which makes this sort of semi-quantitative. This is largely due to the inhomogeneity of these materials in the foams. And so if we could take a big bunch of foam, I'm going to have to get one of those KitchenAid grinders, condense it down into a powder, these numbers would probably improve. Now, another way we use this is on a more well-behaved sample like PVA white glues to do quantitation to help us select products, so choose the lesser of the evils in this case. We're measuring the acetic acid that is off-gassed by these PVA glues. So using acetic acid to create a calibration curve, we get a nice linear curve here, and then we run our EGA analysis looking at Jade 403, which is considered kind of the conservation white glue, both a current formulation and one from about a decade ago. We also ran household white glues as well as shop glues. And when you look at these numbers, they pan out about the way that you would expect. The Jades, which are considered the archival quality PVAs, emit far less acetic acid than the household glues or the wood shop glues. And when you look at our percent errors, they're quite low, again, because these are very well-behaved samples. So if you're going to select a material to use, Jade isn't so bad. And this matches up with what Jane Down from CCI recently published in Studies in Conservation. Well, my third case study, and it's literally a case study, is to talk about that PVC board. So what we were testing is Cell-Tech, and it passed the Oddy test, and we began constructing our cases. Now, this isn't so much about Centra. What I'm really wanting to emphasize here is the need to retest materials that you're regularly buying. So that could be Velar or Ethafoam or Marvaseal or whatever. You Oddy tested it years ago, but if you're not retesting it, and I know that's laborious to do, especially with something that you're ordering a lot of, if you're not retesting it, you could miss formulation changes that might have a negative impact on the artwork, or you might miss that imitator product that has been shipped to you, for instance, the whatever brand under the trade name Centra. So we were ordering a fair amount of Centra for this case design. This is what passed the Oddy test. And when you do the EGA analysis, you can identify two residual solvents here, which show up in the formation of the sheets. And then these other circles here, the blue and the purple, identify these sulfur-containing compounds. They're actually the degradation products of the heat stabilizers that are added to these PVC sheets, so 2-ethylhexylthioglycolates. Now, this material had passed the Oddy test. When we reordered, we got two different lengths of sheets, and investigating found out that the short sheets were Cell-Tech. When we run the EGA analysis of them, it's a mirror image of what we had gotten previously. So we could say, go ahead, fabricate with this stuff, and get going with the project. But the longer sheets actually came from this company, XLFF. And in our 30-minute experiment, you can see that the volatiles are entirely different. They're in fact using a different heat stabilizing compound. This has not been previously tested, therefore it's held in quarantine until the 28-day Oddy test is completed. So this is a way that we hope to be able to more frequently test those materials that currently are just being reordered week after week. Well, I want to end there with some acknowledgements of colleagues at the IMA, current as well as former colleagues, as well as a number of academics and interns who have helped with this work, and also some organizations and groups that have supported our work. And I want to thank you for your attention.